So we're going to look at the planets tonight and what the Bible, or what we can observe as well in astronomy. But I thought we'd start by looking at day 4 of creation and what that tells us about what God did on day 4. Of course, when you read Genesis 1, it tells us that on day 4, God made the greater light, the lessest light, and he made the stars also. Now, for those that don't know, the Hebrew word there for stars, kokav, would encompass not just the stars, but the planets as well. Is that right, Danny?
Yes, generally in ancient cultures, the word for star, it's kokav in Hebrew, is aster in Greek in the New Testament, would refer to any light source in the sky, usually other than the sun and the moon. They generally weren't thought of being as stars. So it would include the planets, it would include comets. The word comet actually means hairy. It's called a hairy star. And shooting stars or falling stars, those are, today we call them meteors, but they certainly look like stars. And you know, the 5 naked eye planets look like bright stars in the sky. The big difference is they move around. The name we get, the word we get planet comes from the Greek. It's planetes aster, which means wandering star. And so we still call the planets stars today. Sometimes Venus right now is called the morning star because it's in the morning sky, will be for another 6-7 months before it becomes the evening star once again. So this idea of separating out and saying, no, the planets are not stars and comets are not stars and meteors are not stars, that's fairly modern. It goes back about 4 centuries. Once the geocentric model was dispensed and the heliocentric model was accepted, and then when people began to build telescopes and look at the planets, they began to make a distinction. But to the ancient world, there was no distinction other than the fact that their motion was a bit different in the sky. So yeah, I think when it says there in the day 4 account, he made the stars also, it's basically talking about every other astronomical body, even those you could not see with the naked eye. Yeah.
And I believe tonight you have some slides to share with us on the planets. So if you want to share those, Danny, we can take a look at those. We're going to look at a number of the different planets tonight, and Danny is going to go through some of them and describe them as we go along, because there are a number of interesting planets in our solar system. I'll let you start off, Danny, by introducing us to the planets.
Okay, do you have that photograph you can see? I can't tell.
Yeah, I can see it. It's on the screen. We can see it.
All right, this is a typical depiction of the solar system that you might see in a textbook. You've got Mercury, Venus, Earth, Mars, and the other planets all lined up there. And I want to emphasize a couple of things. First of all, while the dimensions of the planets are right compared to the sun, the distances are way out of scale. And that's important to point that out. But you can see how big the sun is over on the left, and Jupiter there in the middle. And then the Earth is to the left of Jupiter. And it turns out Jupiter's about 11 times the size of the Earth in diameter, at least. Saturn's about 10 times, and Uranus, Neptune, 04 or so. And so there's a big difference in size. And again, these sizes, relative sizes of all the planets with respect to the sun are correct. Now, what's incorrect more than anything here is the distances, as I mentioned. The distances are way, way, way off. The distance of the Earth from the sun is about 12,000 times its diameter. So you can see the diameter of Earth there isn't very big, but it's only about a matter of maybe 10 times or 20 times its diameter from the sun. And in reality, it's 12,000 times farther away than its own diameter is. And Jupiter is 5 times farther away than that. So if you tried to put this in a reasonable drawing, it wouldn't fit. The drawing would be way too small. The only way to make it fit for the distances from the sun and distances from each other would be to shrink down the sizes of the planets in the sun, in which case the planets wouldn't show up at all. So you have a real dilemma here and try to get this right. Another thing is the planets would never line up all like that. From time to time, 2 or maybe even 3 planets roughly line up, but you would never get all of them lining up there. Now, we can see right away that there's like 2 types of planets. Notice the first 4 are kind of small, and the second 4 are kind of large. And so we use that as a starting point to distinguish between the two types of planets. We call the small ones, the four innermost ones, the terrestrial planets. That means Earth-like. And then we call the four next ones, we call those the gas giant or the Jovian planets. That means Jupiter-like. And what we're saying here is that Jupiter is kind of a representative of those outer four planets, and the Earth is kind of a representative of the inner four planets. And the way they differ is, I mentioned size, but also distance from the sun. As it turns out, Mercury, Venus, and Earth are relatively close to the sun. There's a kind of a gap, and then there's Jupiter and Saturn, Uranus, and Neptune getting farther and farther and farther out. So distance also is a factor. Mass is a factor. The outer planets are very massive. Jupiter is the king of everything in the solar system outside the sun. It takes more than 300 Earth's masses to match Jupiter's mass. In fact, Jupiter has more mass than everything else in the solar system combined, except for the sun. So to a very good approximation, the solar system is the sun and Jupiter, at least when it comes to mass and gravity. The outer planets tend to have lots of natural satellites, or if you will, moons. It's not really correct to call them moons, but many people do. The Jupiter has four large ones, but it has a bunch of smaller ones. Saturn has 4 or 5 large ones, but a bunch of smaller ones. And in total, they can have like 60, 70 satellites each. The Earth has one respectable size natural satellite. Mercury and Venus have none. And Mars has 2 very tiny ones. So in general, the terrestrial planets have few or no natural satellites, and the Jovian planets have many of them. You know that Saturn has a ring system. You can see it there in the depiction. When I was growing up, it was the only planet with rings, but back in the 1970s, they discovered that the other 3 Jovian planets had rings as well. We also know that even though the masses are large, the densities are very low for the outer planets. They're typically 1 or so grams per cubic centimeter. They're all less than 2 by quite a bit. But the terrestrial planets are high. Earth is 5.5 grams per cubic centimeter, as is Venus and Mercury, and Mars is 3.9. Now this, when I was a kid learning this information, it was just kind of boring stuff on a table, and our book didn't really tell us what that meant, but it's very fascinating. You can do a lot of sleuthing in science just by scant information. To have such high densities, we know that tells us something about what the terrestrial planets are made out of. They're made out of rocky substance. Silicate rocks is most likely what you're going to find there. You're going to find some iron and nickel inside the cores of them. You can't have that on Jupiter, Saturn, Uranus, and Neptune, though, because the Jovian planets have such low densities. If they had substantial rock or iron and nickel, their densities would be far, far higher. This is an example, again, how you can reach some very good conclusions in science with just a minimum of input sometimes. We don't know exactly what the compositions are, but we have some restraints or constraints, I guess, on some of what they are. And the reason why we call them the gas giants is because the only substances that will explain their densities are hydrogen and helium. And on Earth, those typically are gases. Now, that doesn't mean they're gases on the Jovian planets, far from it. The outer portions are gaseous. That's kind of an atmosphere you have there. But as you go deeper into the planets, it transitions into a liquid at some point. So much of the interior of these planets are actually liquid. We should call them liquid giants for that reason. But we call them gas giants sometimes because, again, on Earth, the composition would indicate that. So you've got these 2 basic types of planets in the solar system. Again, distance from sun, mass, size, density, rings, planetary satellites. Oh, and one more thing. I know I was forgetting one. The rotation rate. As it turns out, the Jovian planets spin very quickly. Jupiter takes less than 10 hours. Saturn a little over 10 and a half, and Neptune about 16, 17 hours. The terrestrial planets rotate slowly. The Earth takes 24 hours. Mars about 24 and a half hours. And Venus takes a few hundred days, and Mercury takes about 56 days, I believe. So it's a general trend that the terrestrial planets rotate slowly. Now, can we explain this? Well, the evolutionists think they can. I won't go into a lot of detail here. They argue that the solar system formed from a large gas cloud, and as the early sun began to form at the middle, it heated up and blew out the lighter material, the hydrogen and helium. They evaporate at low temperatures and turn into gases, and they were blown out and away from the solar system. but farther out it was colder, and they retained their heavier elements. And supposedly that will explain many of the characteristics, not all, but many of the characteristics. And we creationists don't really have a good explanation right now. We can say that God made them that way, which he certainly did. Why did he make it that way? Well, it's not entirely clear. That's one of my jobs as an astronomer, it happens to be a creationist, is to try to figure out maybe some of the reasons. As it turns out, Jupiter does some protecting of the inner solar system. It protects us from comets and a few other nasty things, which could be a problem for us. And but right now, we don't think we really have a good general broad explanation for these things. Now, sometimes people ask me, well, what about Pluto? It's not on there. And that's a big question people ask. And here's a photograph of me taking, obviously, many years ago. It was over 20 years ago. I was a bit younger, had a little darker hair back then. And this is on the campus of the Lowell Observatory in Flagstaff, Arizona. And it was in 1930 that Clyde Tombaugh, using this very telescope, discovered the planet Saturn. The planet Pluto. And it was hailed as this ninth planet. Lowell and his people have been looking for it for decades. But, almost immediately, they realized there was a problem. It was supposedly found because of gravitational tugs that it was having on some of the outer planets, yanking their orbits around a little bit. But Pluto is very faint and hence very small. I've seen it a few times through a large telescope and hit just a little dot of light. Back for many years, we didn't know much about it, but we now know what its mass is pretty accurately. We know what its size is. And it's pretty wimpy. It takes 400 Plutos to equal the mass of the Earth. The erstwhile smallest planet is Mercury. It would take something like 22 Plutos to equal just Mercury. So there's a big gap there. And many of us for years thought that Pluto shouldn't be a planet. I was telling my students that 30 years ago. I don't think Pluto ought to be a planet. In fact, I predicted to some of my students many times that Clyde Tombaugh was quite elderly. And I said, you watch, after Clyde Tombaugh dies, there will probably be a move to demote Pluto. And sure enough, he died, I think, in shortly after 2000. And not long after that, there was a movement afoot to do this. And it kind of came to a head in 2006. There was a meeting of what's called the International Astronomical Union. It's a group that meets every third year. And they kind of set policies. They have naming conventions, like we have to name things in astronomy, and they have rules for doing that. So they have a lot of things, housekeeping things that they do. And it turns out, Simon, this is interesting. Up to that point, nobody had really clearly defined what a planet is. It's just one of those things that fell through the cracks, and one of those things we know what a planet is when we see it, sort of thing. So never defined. So in 2006, they, for the first time, clearly defined what they thought a planet should be. And it's a large object, three-part basically. The first part was the large object that orbits the sun. And there are many things that orbit the sun, by the way, so you got to kind of qualify that a little bit. But one way you can do that is to note that it has to be spherical. Sometimes people ask, why are the planets spherical? Remember that first slide I showed you? They're all spherical, or very close to it. And the reason for that is gravity. They have enough gravity, it pulls in and forces everything into that spherical shape. And if you could wave a magic wand and turn the Earth into, say, some sort of cube, like I got a box right here, if you could make it kind of box shaped, notice you'd have 8 mountains, 2, 4, 6, 8, and that'd be very far from the center where the gravity is. And they would tend to pull these mountains in and swell out the sides, and pretty soon the Earth would revert to being a sphere again. But if you don't have enough gravity to do that, then you're going to be odd shaped. And smaller bodies in the solar system, we generally call those minor planets, or more colloquially we call them asteroids. They do have odd shapes for the most part, except for a few of them. we have one of the first ones discovered over 200 years ago was named Cirrus, and it actually is a sphere. Yeah. So they said, what are we going to do about that? Well, they said, well, we need to be bigger than just being spherical. And this is where I depart with the basic definition. It's got to orbit the sun. It's got to be spherical, but that's to make it big, but make it really big. And the argument they came up with was it had to clear out the debris from its orbit. And that's getting back to an evolutionary assumption I've referred to. the little pieces come together while the sun's forming and the planets form, and they amalgamate into bigger pieces, which eventually become planets. And Pluto is really in the midst of a field of a bunch of other objects. There's an asteroid belt out beyond the orbit of Neptune. Pluto is just one of the larger members. But the problem with that is there's junk in Earth's orbit too. It hasn't really cleaned it up either. So where do you draw the line on this? So I take a different approach. I simply just arbitrarily say Mercury is the smallest planet by definition. It sounds arbitrary, but all the other definitions are kind of arbitrary too.
Yeah.
And if at first I was teaching at the university at the time, and I had students for years that were upset because they'd fallen in love with Pluto in grade school, and there were third graders who wrote hate mail to some astronomers over this back 13, 14 years ago. Big emotional attachment. I never understood the fascination with Pluto. I think it may just be the fact that it was mysterious, never seen up close before, and so it could be anything that you want it to be. That's changed now, of course, but since the last 14 years, we've had a whole new generation of people come down the pike. You have to be at least 20 years old to remember that, to have any recollection of Pluto ever being a planet. So we've kind of gotten over that. You don't get students arguing with you quite so much anymore. And we've actually been through this before. I mentioned Sirius. It was discovered in 1801. And when it was discovered, it was called a planet. It was people were expecting a planet between Mars and Jupiter, just like they expected a planet beyond the orbit of Neptune. And so when they found something, they thought this is the planet. And they found a few more. And for several years, about 40 years, they thought they had 4 or 5 little tiny planets between Mars and Pluto. It was around 1845 before they finally settled and said, look, these aren't planets at all. These are asteroids or minor planets. So now we've reclassified Pluto as an asteroid or a minor planet, but we have created a special category for it and 4 others. They're called dwarf planets. They're objects that are spherical, but yet small enough, big enough to be small enough not to be considered a planet.
Danny, there's a question. Did Pluto once have an ocean on it?
Ah, boy, that's an interesting question. I don't think so. There's been several items in the news recently about a possible ocean at one time on Mars. In fact, this past week, I think, or the last few days, there's been one in the offing. And I actually wrote an article about this recently. I'm not sure if it's gone up yet. I'll have to check, but if it's not on our website yet, it will be. People can go to answersingenesis.org and then just type in Pluto and get some hits on these things. It's interesting. Let me show you a picture of Pluto. I'll step out of this and find it. I'm going out of order here, but I think we can do this. And there it is. Y'all see it?
Mm-hmm. Yeah.
Mm-hmm. And this was taken by the New Horizons mission, 5 years ago, 2015. And this was quite a surprise. It was a flyby mission. And when it did, they were expecting it to be heavily cratered. And I'm going to come back and talk about craters here in just a minute. I got some slides about that, but since we're jumping ahead a little bit, it's okay. They were expecting to be heavily cratered, and I'll explain why in a few minutes, but yet there are relatively few craters there in some places. Some places to the upper right, there are some, and to the upper left, but there's a big heart-shaped region down near the lower right. That region is almost totally void of any craters, and that's pretty common across the surface. Pluto, as it turns out, had far fewer craters than generally thought. And that has caused people to suggest that there's much more geology has gone on in Pluto than they originally thought. And they've suggested that there may, even this article came out in the last few days, suggested a subsurface ocean of some sort today on Pluto. Now, it wouldn't be liquid water. It's way too cold for liquid water. It would be some other substance down there that's frozen methane or liquid methane or something like that. So we're reevaluating and talking about Pluto quite a bit in astronomy circles.
There's another question that's coming. Can we jump to that quickly? Someone's asked, how do evolutionists explain the fact that Venus spins the opposite way from the other planets?
Oh, that's a good question. That is believed to be a late hit. Remember, I talked about how the solar system supposedly formed 4.5 billion years ago. It's a large gas cloud that slowly contracts. And as it contracts, much of the material fell to the center and formed the sun. And then the remaining material, what little there was left, flattened out into a disk. And as the sun is starting to heat up, the stuff inside this orbiting disk of material begins to coalesce. The small particles begin to stick to larger particles. They get bigger and bigger, and eventually they got enough gravity they can pull pieces in to make bigger things, and eventually end up with a planet and satellites of the planets and so forth. And stuff that never got amalgamated are asteroids, and these things occasionally hit the Earth today and other objects in the solar system and cause a meteor in the sky, or maybe an impact on the ground if it's large enough. So the idea is, as Venus was forming and nearly formed, it's sitting here spinning. It's the same direction that the solar system spins. You get above the North Pole and look down, all the planets are orbiting in a counterclockwise direction around the sun, and most planets spin in a counterclockwise direction too, except two of them. Uranus and Venus both spin backwards. So the idea is that Venus originally was spinning the right way, and then as it's spinning this way, it got hit by a large thing on one side. On the other side, this had a head-on collision as it was spinning and reversed that spin. So you had a couple of late spins, late collisions to do that, one for Venus and one for Uranus. The problem with that is if you're going to invoke that, in order to reverse the direction, it's going to have to be a very large impact.
Yeah.
And if you have a very large impact, it would tend to alter the orbit of things. You just can't just slam into it and not leave the orbit unaffected. It's going to change the orbit. And if you randomly inject energy into an orbit, it will tend to move the orbit from being circular to being more elliptical, from being circular down to a flattened sort of circle, what we call an ellipse. And if you look at the orbits of the 8 planets, guess which 2 planets have the most circular orbits? Venus and Uranus, the 2 that rotate backwards. It's amazing how that works. So you look at the rotations, and the evolutionary viewpoint is say, well, late large collisions explain this. But then if you look at the orbits themselves and ask, well, which planets of the 8 actually had large late collisions? The last 2 on the list would be Venus and Uranus. Their orbits don't match what you would expect if you had such late collisions. Uranus is even more of a mess. People won't talk about it much, but it rotates very quickly, Venus very slowly. And it's skewed over. It's not just orbiting like this. It's tilted so that it's tilted 98 degrees or 82 degrees from perpendicular and going backwards. And so the equator is like this, not like that, or even tilted a little bit. And what's interesting is it's got a system of natural satellites, and they're orbiting for the most part in the equatorial plane. So they flipped over too. And to do that, you wouldn't need a single large late hit. You actually need 2 with some sort of recovery time in between, minimum of 2. It actually could be more than that. So you're starting to compound the problems repeatedly here, and you begin to realize you have a problem. It's almost as if God was maybe just a little playful here. And so I'm going to give you a couple here that'll be hard for you to explain. So anyway, I love talking about Venus and Uranus because they do kind of foul up the evolutionary assumptions.
Do you think they have a purpose then, or is there a reason that we know that you got, as creation scientists would say, they rotate the opposite way?
Yeah, I think, I don't know of a purpose that would serve, but it seems to be, to me, one of those just little design things that God put in there. I think sometimes maybe he hides things in plain sight. If you're paying attention and you don't have the wrong worldview, you can actually say, aha, I see what's going on here. These 2 planets really defy naturalistic explanation unless you really want to invoke a lot of improbable events. And one question is, how many improbable events are you allowed to have? That's my question for evolutionists in general. All sorts of weird things that they have to invoke that happen. And just how many of these are you allowed to have? How many coincidences are you allowed to have before you begin to realize that maybe it isn't a series of coincidences at all? So I think that could be the reason why God did them that way.
Someone else has asked a question. It's a good one to think about. They've asked, how do flat earthers explain that the other planets are spheric and not the Earth?
Oh boy, they're all over the place on that one. They would, some of them would argue that they're not spherical just because they look round. It doesn't make them round. They could be pizza pan shaped. And then the others would say, okay, even if they are spherical, what does it matter? It doesn't prove anything about the Earth. I mean, when you say that because the planets are spherical, the Earth must be spherical, that is an argument by analogy. And it's a weak argument. It's an argument worth making, but it is a weak argument, I will admit. And so you have to assume that somehow the planets are like the Earth. But you see, flat earthers don't agree with that at all. They believe the Earth is ultra unique. I mean, I think the Earth is unique too. It's a unique planet. They would say, no, its uniqueness goes far, 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 far beyond that. You can't draw any conclusions about the Earth by looking at the other planets. So that would be how they would respond to that.
So would they even believe that there are other planets out there and they would recognize them, or do they try and say it's a cover up? Or
well, again, they're all over the place. Most of them say that the planets are just lights in the sky. They're just stars or wandering stars. And I like to talk about the Book of Enoch, talking about wandering stars and saying they're fallen angels and so forth. They have some pretty bizarre attitudes about, bizarre opinions about what the stars are too. You can't really talk about just what flat earthers think of the planets without talking about the stars as well. In short, virtually everything that astronomers tell you about the universe is wrong. So once you do that, then you can say whatever you want about these things now, can't you?
Yeah. And should we go back to your slides? Do you have...
Feel free to interrupt me with questions from viewers or questions from that you have. If you have a question, you don't be afraid to stop me either.
I'll ask. I was going to ask you about the big hurricane on Jupiter, but
the great red spot.
Yeah.
I don't think I have a picture of that today, but the thing about the great red spot is it's cyclonic. It's swirling around the same right direction it should for the hemisphere that it's in. So it appears to be a low pressure system. And interesting, there are other spots on Jupiter as well, and they're spinning around too. And you've got these bands that move very quickly. On the Earth, we have three major bands: the equatorial, and then the tropical, and then up in the Arctic region. So you got directions, the trade winds and prevailing westerlies, and then the Arctic. They reverse direction a couple of times. That's caused by the Coriolis effect, by the Earth's relatively rapid rotation. Now, the large planets are rotating even faster, and they're big planets. So it's a tremendous Coriolis effect they have. And it's so extreme that you don't end up with these graceful arches and swirls. You end up with bands going like this with high winds between them, actually, very hurricane force winds between different bands on the planet. So in between, you've got these storms going around like this that look like little ball bearings. Time-lapse videos of these will show little ball bearings spinning like the red spot does. And we thought for a long time the red spot has been a persistent thing. It was first observed by a guy named Cassini around 1650, so it's nearly 4 centuries. The thing fades from time to time and then flares up from time to time. It's virtually disappeared, but it has come back about the same location. Unfortunately, during most of my lifetime, it's been kind of wiped out. It's been very muted. 50, 60, 70 years ago, actually, it was much more intense. But since the early 60s, it's been kind of wimpy. And to tell you the truth, I've not seen it that often. And the times I have, it's more like a little gray spot. I kind of wish I was maybe born a little earlier, so I could have enjoyed it better, I guess. But it is spinning around, and we don't know if there's precipitation going on like in a hurricane, but it is a low pressure system. We can tell by the direction it's rotating that it is. Not a high pressure.
So it does speed up and slow down.
No, it just keeps spinning all the time. I can't say that the airspeed changes much. I don't know if we know enough about that to say that, but it is like a hurricane sitting there parked for hundreds of years though.
Okay, just to remind viewers tonight, if you do have a question for Danny on the planets, on the solar system, then please do put it in the comments section and we'll try and get to it. I'll ask this one quickly. You'll probably know the answer to this. Someone's asked, how many people believe in a flat Earth?
Around the globe, there are probably a few million people now. It's been a growing movement. I think the growth has slowed recently for a couple of reasons, but it is a very vibrant movement out there, and it's a dangerous movement. We did a show on that recently. I think it's the reason why the questions keep coming up here, and people are interested in it. And we do have a couple resources there. We have the book, my book, Flat Earth, Falling Flat, Refuting Flat Earth Arguments. And do you sell the DVD there of Faith on the Edge? I don't know if you do or not.
Yeah, we do. We've got that DVD. You're in that DVD.
I'm in that DVD. But anyway, those are two products we do have, and we have numerous articles on our website. So anyway, that's I don't know the exact figures, but I wouldn't be surprised if it's not a couple of million people at this point around the world. Okay, here I have a photograph of the moon, and most people could readily recognize it because, well, you tell me, Simon, what do you see that makes you think it's the moon?
Well, the color and the craters on the moon.
Okay, lots and lots of craters. That's the first thing that Galileo saw with his telescope 4 centuries ago, and it just blew him away. What is this? And there was quite a bit of debate for hundreds of years about the source of craters. It really wasn't settled in the 1950s, I guess, with just short before I started really paying attention to stuff. I was born, I guess, when they settled this, or about the time they did. And the two basic theories were volcanic and impact. The volcanic is basically, these are calderas or fumaroles, different. There are some volcanic features that leave craters behind, features that are volcanic in origin, I should say. But many others are impact. And today we think the vast majority of lunar craters are impact, but there are a few smaller ones we're pretty certain are actually volcanic in origin. So we sort of split the difference. But any crater you're going to see with a telescope probably is going to be impact. All those ones you see there are impact. But it's not unique to the moon. Here's one I like. This is from Mars, put together by some Mars orbiter. Everybody likes that. See a little smiley face down there?
Yeah.
Mars. It was quite a shock back in 1965. The first spacecraft to fly past Mars and take photographs. They photographed a few percent of the Martian surface, and they saw all these craters. And most people were not expecting that. And they went from what they thought was a somewhat Earth-like planet to a lunar-like planet. That was a little extreme. As it turns out, they just happened to sample a heavily cratered part of Mars. There are places that are less cratered than that. So it's a very complex world, but it does have lots of craters. And Mercury has craters on it. In fact, Mercury, it's hard to tell the untrained eye from the moon. This one here is one of my two favorite satellites or moons in the solar system. This is Mimas. It's one of the larger medium-sized satellites of Saturn. And this is a high resolution from the Cassini mission. The earlier ones from the Voyager weren't such high resolution. And you see that large crater there? It's called Herschel. That's what they call that. And back before the Cassini pictures, the photos we got, it looked a lot like the Death Star from the Star Wars movie. And I always got a lot of kick out of that. I'd show up slides in my classrooms, and then I put the picture of the Death Star up, and people just start laughing about it. It was really pretty funny. That was nice when it was not much to be seen, but now that we have much better reconnaissance like the Cassini mission, it doesn't quite resemble the Death Star as much. What's interesting, Simon, is they have a difficult time explaining this size of this crater, because they can run the numbers on this, and something big enough to smash into Mimas and make a crater that large has enough energy really to shatter this thing. And so trying to figure out how this crater happened is tricky too. And it's really kind of on the edge of being able to be explained.
Danny, have we ever witnessed a meteor or impact hit the moon or another planet?
Yes, I'm going to show you one of Jupiter back from 1994 in just a minute. But in the last few years, I'm talking about the last decade, people have taken high-speed cameras and that didn't exist before, putting them on the telescopes, good-sized telescopes that few amateurs had before. These are amateurs doing this for the most part. And they've particularly been looking at the moon during meteor showers. We know the Earth is being pelted, so why couldn't the moon be pelted? And people have actually documented a number of flashes of light on the moon now that they think are caused by meteor strikes. So 20 years ago I couldn't say that, but today I can. That we do have definite evidence. We've actually seen these things or witnessed these things forming.
I think I read something, and you can tell me if this is true or not. In Canterbury, in England, some medieval monks saw part of the moon explode or something.
This was about 1200, I believe. I forget the exact date, but it was medieval time.
1100.
And monks what's that?
1100s, I think.
1100, okay, off by a century. 12th century, I'll put it that way. How's that sound? And height of the Middle Ages, and some monks actually did witness something in the moon. It's a crescent moon, and people have investigated that, and they're thinking it may have been a very large impact that occurred at the time. If it's big enough, you can see it with the naked eye, which telescopes didn't exist yet. That would be a pretty good size impact to do it. So yeah, if you count that one, then we even have more earlier data. That's a bit controversial. The more recent ones, smaller impacts, are not controversial at all, really. All right. And here we have one of the satellites of Mars. I can't remember which, but you can see craters. I used to show this to my classes, this and many other photographs, and you start seeing a theme appearing. Here's Vesta. This is one of the asteroids out there, one of the big four, and it's not quite circular like Sirius is, but it has impact craters on it as well. We've seen impact craters now. We've done some reconnaissance of some comet nuclei, and they have craters. And we look at, every time we look up close at an asteroid, it has craters. So we see it again and again. You ask about Jupiter. Here is an impact of Jupiter back in 1994. Comet Shoemaker-Levy 9 slammed into the planet. And
is that at the top? Is that at the top? Is it
that black eye up at the top? You see some
Okay.
other white spots. Those white spots are some of those other spots in the atmosphere of Jupiter. And here's what happened. 2 years before, a comet came close to Jupiter on the way in from way out. It was coming towards the sun, passed very close to Jupiter, and the tides raised on it by Jupiter. Remember, it's got a lot of mass, shredded it. And a few months later, someone actually discovered the comet, and it wasn't a single one. It was like a string of pearls, a bunch of little tiny nuclei in a row in its orbit. And they ran the orbit back, and they said, aha, this thing had an interaction a few months ago with Pluto on its way in, but nobody knew about the comet yet. So they knew where it was. They just extrapolate back from the orbit. The line of debris orbited the sun and shot back outward again. And so happened on the way back out, it was on a collision course with Jupiter. And the collision actually was behind the planet. You couldn't see it because it came up behind, but they used the HST, the Hubble Space Telescope, to take this image and others. And what would happen is the impacts would occur on the backside of Jupiter, and then as it spun around within an hour or so, you could see the impact point. And I used a relatively modest backyard telescope to look at Jupiter at this time, and you could see these little dots. You didn't need much of a telescope at all to see them. It was amazing. And in 400 years of telescopic observation, we had never witnessed anything like this before. So
Wow.
we felt very special to be at that time. Lest anybody be concerned, within a few weeks, all of that cleared up, and Jupiter was no more worse for the wear. But that impact site there is probably close to the Earth size, and it just shattered out through the atmosphere some distance. So we've seen impacts. You ask about that. Here's Jupiter almost 30 years ago.
And that's the size of the Earth. That impact.
Close to it. Remember, Jupiter's 11 times the size of the Earth. So if you work out the diameter there, it's getting close to being Earth size there.
That's a big impact. Yeah.
Yeah. Now the impacting body is pretty small. It's only maybe a mile or two across. We're talking about an atmosphere, so you got like shock waves that go out, maybe precipitate out stuff, and it makes a much bigger mark. And that's a good thing to point out on the surface of like the moon. You see a crater 10 miles across, it doesn't mean that the impacting body was 10 miles across. In fact, it was probably far less than a mile across. The impacting body, the impact of the crater left behind is always far larger than the impacting body itself. It's the kinetic energy released when it strikes that makes that large crater. Kinetic energy is the energy of motion. If you have a projectile, such as a bullet, that's at high speed and it's mass that caused the damage, and so when it hits, it's gonna do a lot of damage on the surface of a planet. And the Earth is not immune. This is the Arizona Meteor crater. I've been there several times. Back about 15, 16, 17 years ago, a friend of mine from college was a pastor in Phoenix, and he had a light plane, and he took me up for a couple hours flying over northern Arizona. That was a lot of fun. And we flew over Meteor Crater, and a lot of the good pictures are copyrighted. Well, this one's my own photo, so I got complete access to this one. And I've been on the ground a number of times. You can see there to the lower left of below the crater, there is a road coming in. It's a 2-lane road, and there's a large parking lot and a large visitor center there. That crater is nearly a mile across. and about 600 feet deep. I went the first time on this about 23 years or so ago, 24 years ago, my first trip out there, and I went to Grand Canyon. It was good. It was grand, but not what I expected. But this was bigger than what I expected. It really is. It's an amazing place.
Are you allowed to go into the crater?
Down into it, no. You can take a walk for about a half mile out to that point about the middle of the foreground. You can see a little trail if you look very carefully along the rim between to the right of the visitor center. There's a little white trail. That's the trail that you can walk on. Years ago, I understand you could take a trail down to the bottom, but I think it's kind of strenuous because the side is so steep and liability issues, and plus people were wearing away the sides of the thing. It's in a desert environment. Here, I took the walk. There's my observing research partner, Ron Samick, and I standing on the rim, so you can see down the bottom of the crater there.
Wow. So when do evolutionists date that to, and when would we as creationists date it to?
Oh, it's interesting. At one time, they were saying this happened like 1 million years ago, then 50,000 years ago. They keep shortening it and shortening it. They now say it's thousands of years ago, but it's interesting. There was a big debate about this, in the 19th and well into the 20th century. It wasn't until the 1950s that a geologist named Gene Shoemaker finally resolved the issue. Gene Shoemaker had been over in Nevada, where they had a testing ground for nuclear weapons. They had detonate them under the ground, and it would make a big crater. And he was measuring the shapes and depths of these craters and widths of them, and working out a relationship between the energy. He knew what the energy release for each one of them was, and he studied them quite extensively. So while he was there, he decided to drive on over to Arizona and take a look at this. And when he did, he said, this looks exactly like the impact crater, the detonation craters I've been looking at in Nevada. The only difference is this thing's really, really, really big. So he could scale it up and calculate how much energy was released and roughly how large the impacting body had to be. Up to that point, most geologists had said it was volcanic. There are volcanoes in northern Arizona. So it was a big, big debate over all of that. And in retrospect, I can't imagine why anybody ever thought it was a volcanic crater. It doesn't look anything like them. A lot of features, we could go into detail on that, but it's not terribly important. But
so when a meteor would cause that impact, what happens to the meteor? Is it totally obliterated? Is there anything left of it?
Yeah, that was one of the arguments the volcanologists used. They had you see that white spot in the right side there in the bottom of the crater?
Yeah,
that's talus from tailings from where they drilled down. They drilled down in the bottom, went really deep, looking for the iron that they thought would be there. Never found it. And then off to the right, near the edge, there's a slight asymmetry suggesting it came in at an angle, and they drilled down really deep, never found it. But for miles around, they found tons of debris. I've got a piece of it about this big in my own possession. I bought once at a rock shop, and they sell soil there that you can run a magnet through and pick up little tiny round spherical balls of iron. It basically rained or hailed iron particles for a while. What they believe happened was a meteoroid maybe 50 to 100 meters across, okay, 50 to 100 meters across, entered the atmosphere, streaked through really fast, and hit the surface and went down a few hundred feet, where it finally slowed down from just the earth being in the way. And when it did, it had to release all of this kinetic energy, so it exploded. And it blew layers out. You see that red rock I'm standing on? That's called the Coconino sandstone.
Oh wow!
And it's actually a layer below the. That's the Moenkopi sandstone. The Coconino is actually below that, and the Coconino is at Grand Canyon, but not the Moenkopi. The Moenkopi is on top here, and it got flipped back like this. And so when you see that, you walk up the there's an elevated raised rim. As you go up there, it's all Moenkopi, and then there's upside down Coconino, and then upside down Moenkopi again. So it's been flipped out and debris thrown for miles. And so the thing exploded. That's the reason why you don't find any inside. This is what's really interesting. They had this debate about where it came from. You know, as a meteor, as a volcanic crater head, and Gene Shoemaker finally settled that 60 years ago. But had they actually bothered to ask the Hopi and the Navajo that live there, their ancestors have been there for a long time, they had a story about where this came from. You want to know what the story was?
Go on.
Some big thing came out of the sky and hit the ground. So it's pretty certain, I think, that otherwise, they would have had some great spirit to gouge us out, or a big buffalo or something. No, they gave the perfect description of what we now believe to be the origin. And I think it's pretty clear that their ancestors probably witnessed this. It'd be one of those things I would have liked to watch from about 20 miles away. That would have been pretty cool. I wouldn't want to be any closer than that. But
so can we date it as creationist? Do we say it? I mean, it's not something that would have been part of the flood. It's after the flood?
It would have been post-flood for sure. But northern Arizona has tremendous stuff. It has Grand Canyon. It has Meteor crater. It has volcanoes. It has like 800 cinder cone volcanoes. The San Francisco peaks go up a mile. It's the highest place in Arizona. It's really a wonderful place to visit, and a lot of things to do. They have Indian ruins you can go to. It's I love Arizona. Just a lot of neat things to see in Arizona. So the Earth even has been hit by meteors in the past as well, though not as many as you'd find on some of the other planets. Now, you look at Pluto, and I guess getting back to what we're saying about Pluto, the idea is that the planets have been being hit by these things since the beginning. And early on, they were still being formed. They were being hit a lot because they're collecting these little particles called planetesimals to build bigger and bigger planets. But every time one of these planetesimals slams into a planet, it's one less planetesimal out there. And so with time, the amount of little debris left over, we get less and less and less. And so a lot of the impacts would have occurred early on. We're talking, 4 billion years ago, or even more. And then things kind of settled down on the moon. They kind of dated it all. They have an event they call the early and late heavy bombardments. And that all ended like 3.5 billion years ago. So for the first billion years, things were chaotic. But about 3.5 billion years ago, things have settled down. And so we still get impacts, but not nearly at the rate we once had. Except, why don't you find a lot of craters on the Earth? Well, I would argue it never had as many to start with. It had some, but not as many. But the argument they would give, the evolutionists would give, is that the Earth is geologically active. You have plate tectonics, you have volcanic activity, you have weathering, all these things going on. And as you do that, you grind the surface over, resurface things, and recycle things with plate tectonics to the extent that all the primordial craters are long since gone. But on less geologically active bodies like the moon, they still preserve craters from early on. Many of the craters you see on the moon are thought to be 4 billion years old. The youngest ones typically are 3.5 billion years old. So the Earth doesn't show those because we have a lot of geological activity that the moon never had, or had very early on, but lost very quickly. Mars has a lot of craters because it's more geologically active than the moon has been, but less than the Earth has been. Okay, what drives the geology? Well, generally it's heat inside of a planet. It's heat that makes those plate motions move around and slide across the surface. If you lose heat, and you'll do that through loss, radiative losses over the years, then you would expect then that the geological activity would slow down. And the Earth is unique among the terrestrial planets, perhaps, or nearly unique in the fact that radioactive decay is supposed to have driven that. You need heavier elements to do that. But smaller bodies, they leak away that heat quite a bit. There are some exceptions. For instance, Io, that's one of the natural satellites of Jupiter. It doesn't have any craters at all. I always get hungry. This is my other favorite satellites in the solar system. I get hungry when I look at it. What does it look like to you?
It looks like takeaway pizza.
It looks like a pizza to me. I can see some cheese and maybe a little sausage on there, tomato sauce and so forth. And so it's a very volcanically active world. They actually discovered back in 1979 with the Voyager probe, they discovered the plumes of volcanoes erupting. And the Galileo probe spent several years orbiting around inside of the Jovian system more recently. And they documented a lot of volcanic flows. In fact, they showed, there's comparisons of photographs of locations taken just a few years apart, and they're totally almost unrecognizable because it all gets resurfaced. So Io is very volcanically active. Now, keep in mind that on Io, at least, the volcanic activity there is not molten rock like it is on Earth. It's actually molten sulfur. That's why you get these yellow and red appearances on the surface of different sulfur compounds. Now, when you get very hot sulfur, you know what that's also known as, Simon?
No.
Brimstone.
Oh, okay. Yes. Yeah. Yes.
So I can say that Io smells like hell. I'm not cussing. I'm just being very descriptive. If you went there, it wouldn't smell too good. You have that rotten egg smell of brimstone. It'd be really pretty bad. At any rate, the surface is being the surface is being redone all the time. Now, here's the question: what's driving the heat on Io? What's keeping it geologically active? Because it's more geologically active than the Earth, yet it's much smaller. Any primordial heat should have leaked away a long time, billions of years ago. And it lacks the heavier elements. We know from the density, it doesn't have the heavier elements to produce volcanic activity. So it needs some other heat source. Now, the argument usually is made, its orbit's close to Jupiter, and they argue, the evolutionists generally argue that it's tidal interaction, flexing the planet. It comes a little closer, a little farther away, and so the planet, the little body does this. I can't call it a planet, it's not, it's a satellite, but it does this. And it's like a piece of metal. If you flex the piece of metal, eventually it will heat up and can break after a while, just from the friction that you put into it. So I think it's frictional heating going on here. The only problem is we had a creationist, one of our creation scientists, Wayne Spencer, examined this quite thoroughly a number of years ago, and he found out the mechanism really doesn't work very well. It's just not efficient enough. So it's still a question: where is that heat coming from? But go back to Pluto. Go back to Pluto. It's very light. It has no heavy elements to speak of. It's very far from the sun. It's very small. It doesn't have an internal heat source. So where did it get its internal heat to drive fairly recent things upon it? That's why it's a surprise. They were expecting it to be dead as a doornail, far deader than geologically speaking than the moon is. Yet it shows evidence of being much more geologically active than the moon is, and many other objects in the solar system. So they've been scrambling the last 5 years, rewriting the textbooks on Pluto. It really, one of those things that may defy explanation on all these things. While I'm talking about heat, I can move on to some of the outer planets. Here's a photograph of Neptune. Turns out 3 of the 4 Jovian planets release more energy from the sun than they receive. In some cases, it's 2 to 1. They're putting off twice as much energy. It's in the infrared part of the spectrum, still bleeding off heat. And these things can conduct heat at a certain rate. We can calculate that pretty well for what we know about the size and structure and composition. And it turns out the Jovian planets should have lost all of their heat a long time ago, if they're billions of years old. And there is no known mechanism whereby you can heat this. They've tried everything and they have no solution as to the internal heat of these things. And again, interesting, it's three of the 4. Uranus is the odd man out, and Uranus is odd anyway. Remember, it's got that weird tilt to it, and it's got a circular orbit. So why do 3 of the 4 have all this excess heat? Where did it come from? Well, we creationists have a solution for that. We don't think it's that old at all. God created it fairly recently, and they've just not simply haven't drained all their heat off yet. Why does Uranus not have that heat? Well, we don't know. It just, for whatever reason, God decided to make it cold for some reason. We don't know what that reason is yet.
Danny, regarding the planets and the names of the planets, obviously they get their names from Greek gods.
Uh-huh.
Do we know the purpose behind that, or who named the planets?
Well, the ancient astronomers named it. How they named those is up to debate. The names we have came from the Romans. The Greeks had their names, Aphrodite and so forth, Hermes and Zeus.
Yeah, sorry, Roman gods.
Yeah, so they had their own names for them, and that probably was pretty common among them. And don't forget the word sun and moon are also in most languages are names of gods as well. Mm-hmm. Sol in Latin, and Helios in Greek, and Luna in Latin, and Selene, I think, in Greek. Those were all gods as well. And I think it's because they recognize the importance of the sun and the moon. You know, the sun every day rises and sets, and it keeps us warm, and it produces light for photosynthesis and other things. The moon also has an effect on the tides because it gives us a calendar to work from. We've talked about before. And then there's the planets are moving around in the sky, very different from the stars. The stars move throughout the night, but they come back tomorrow night about the same location at the same time. They change seasonally, but they come back next year at the same location. The constellations look pretty much the same as they did thousands of years ago, but the planets move. They move obviously through the stars. So they got the thinking that the sun and the moon were gods or manifestations of their gods. And then while you're at it, you've got these weird objects that are doing funny things. Maybe they're gods too. So it goes way back into pagan history when, you know, early on, God revealed himself to man, but man rejected that. And when you reject the truth, then was it Chesterton who said, when people stop believing in God, it's not that they believe in nothing, but that they'll believe anything. And that's very apropos here. I think it's because, you know, people start looking for alternate gods, and why not have something you can see in the sky to do that? So I think that's where the names came from. Some people try to make a deal out of that, you know, saying there's some significance here, we shouldn't be using those. But, you know, the days of the week were named after those same gods. Right. And there are many things, you know, when people sneeze, they say Gesundheit or God bless you. You know what? That is a pagan idea too. So we've got all sorts of pagan things around us. June, you better not get married in June, because that's a pagan thing too. We need to live our lives without guilt. We're not pagans just because we happen to use a name that has a pagan origin. If you really are a pagan, that's a problem. But I'm not a pagan, you're not a pagan. So just because those names are there, it's convenient to use. If you want to try changing it, lots of luck with that.
Yeah. I think we've got a question that came in a few minutes ago, someone who just joined halfway through, and they asked, do planets require moons?
No, they don't. Mercury and Venus don't have any, and Mars barely has a couple. They don't really matter too much. Now, the Earth, there's a lot about the Earth's moon. It's amazing. We use it for time reckoning the month, but also the tides are important. But the moon's existence, maybe we can talk about this in a future show. We may not have time to talk about it today, but the moon's unique large size and its unique orbit actually stabilizes the Earth's rotation axis. So there's a design aspect there. So yeah, I think the moon is a design feature just for the Earth. If the Jovian planets have satellites for some reason, well, I don't know what that is yet sometimes, but I think in one case, the special case of the Earth, yeah, it does require a moon.
Yeah. If anyone else has a question who is watching, I know we've got another one, then please do put it into the comment section and we'll try and get to it. It's regarding, Danny, the rings on Saturn. Do we know what they're made up of, and have they always been a part of Saturn?
Yeah, they're small particles. They're actually just billions and billions of small particles. The rings are tens of thousands of miles wide, and then twice each orbit, about every 15 years, the thing goes edge on, and when it does, the rings disappear. I've seen Saturn several times now where there were no rings at all. Wow. And that indicates that the rings are very thin, maybe 100 meters thick at the thickest. And when sometimes Saturn will pass in front of a bright star, and it's called an occultation. And when it does, you can see the light of the star shining through those rings. So they're not solid at all. There's actually a lot of room in between them, and they're all orbiting around. Now, where did that come from? Well, one theory is that if a planet, if a satellite it's held together by gravity, it's key. It's got to be held together by gravity. If it gets close enough to Saturn within what's called the Roche limit, then tidal forces on the planet will rip it apart and spread it out. Now, if it's held together by other things like cohesive strength of, holding it, like a brick is held together, that's a different story. But if it's big enough to have gravity, it will be shredded. So the idea is that the rings of Saturn happened when a satellite in the past got too close and got shredded and turned into a satellite, to a ring system. Thing is, ring systems are very dynamic. They don't last very long. Different estimates now, but they're all very short-lived. A million years might be an outside figure for that. So we know the rings of Saturn are very young. We know the rings of the other Jovian planets are very young. That doesn't mean the solar system is young or those planets are young. However, we have to believe then, if we think of billions of years, that we happen to be living at a privileged time when all 4 Jovian planets recently disrupted each one disrupted a satellite. And that's pretty hard to believe. Just how many satellites did they have and how long has this been going on? So we either those planets are and the rings are very young, or we're just living at a really peculiar time with lots of coincidences. And again, as I said earlier, how many coincidences are you allowed to have?
Yeah. If you're an evolutionist, you seem to get a lot of them.
Yeah.
Do you think they were designed that way with rings, planets?
I think so. My own attitude is I think the Lord put them there to defy what man wants to think in this late date. It wasn't until recently, in the last few hundred years, we discovered the ring systems, but now we even know that they don't last very long. And I think why would not God do that? Why would he not leave little clues out there saying, hey, try to explain that, Mr. Billion of Years guys? And I think that could be evidence staring you right in the face that the universe, the world, the solar system is not nearly as old as people think.
Okay. We'll end with this question. We've been going past an hour now and it's been really good. What's the best planet to observe from the Earth?
Oh boy, tough question. Venus is fairly easy. It's in the morning sky right now. If you go out before it gets light, before it gets totally light, it's got to look at it kind of late, a half hour, maybe 45 minutes before sunrise. It's near the sun. It's a very bright object. If you have a telescope, look at it. It's a big, thin crescent. It's beautiful to look at. Over the next few months, it will get farther from the sun, but it will shrink in size and thicken up. So it's a really cool planet to look at. But my absolute favorite planet to look at is Saturn. I first looked at it over 50 years ago with a small telescope, and I could not believe what I was looking at. I could see the rings clear as could be. And I've never gotten tired of looking at Saturn. It's always a treat for me. It's always a delight to see it. Saturn is close to Jupiter. It now, both of them rise not too long after dark. They'd be over in the southeast in the evening sky. Jupiter's very bright. It'd be the brightest star in the sky. Saturn is to its left, not quite as bright. If you have a small telescope, try looking at it. It takes about 30 magnification or so to make out the rings. I'd go a little higher if you could, but it's a stunner, I think.
Yeah. There's one more question come through. We'll try and hit this and end with this one. Someone has asked, is it conceivable to believe hell, Hades, is in the heart of the Earth, as it is very hot down there? What happens in the middle of the Earth? Is there a dynamo or something to generate energy? And that might have been generated because of Io planet that we looked at.
Yeah, the dynamo is usually thought of as being the source of the motion in the core to produce the magnetic field. That's a different issue. It's I would think it's residual heat. It's also a combination of that and some radioactivity going on as well. As far as it being the location of the lake of fire, people confuse hell and lake of fire many times, unfortunately. Hell is the grave, lake of fire is the ultimate punishment. People long believe that it's down there, but I tend to think not. It seems to not fit with the new heaven and the new earth. I think it's a special place prepared, and I wouldn't be a bit surprised if it's someplace else entirely, just like heaven is someplace else entirely.
Yeah, I think in Matthew 25, Jesus does say it is a prepared place. Yeah, it's probably a